Good day. Today's screencast is about compactness. We're going to talk about compactness in class, and there's two types of compactness that we'll talk about in class. One, sequential compactness, and the other compactness is a way of defining the property inside a Euclidean space. And in that context, you can say a set is compact if it's closed and bounded. What I want to talk about here, and I'll mention this other way of looking at compactness in class, but I'm not going to say too much about it. But what I'm going to talk about today is another definition of compactness. It looks like this. So a set F in R is compact if every open cover of F has a finite subcover. So this is a very topological way of talking about compactness, and it's pretty abstract. So I wanted to make a screencast just to talk about this, let you watch it on your own time, wrap your head around it, and we'll probably refer to it maybe once or twice this semester. But the other two ways of defining compactness are going to be more immediately useful for us. But what I want to talk about today is, in the screencast, is explain what this means. Every open cover has a finite subcover. I mean, this is how compactness is characterized in this topological definition. So let me explain these terms. So here's a definition. And this conversation or this discussion is going to be pretty notation heavy, and so this is another benefit of doing this as a screencast, so you can go back and take a look at this several times if you need to. So a collection of sets, I'm going to write that U, and I'd like to draw this U as a script. U, which is a set of U sub I, and each of these is a set of real numbers. And I here, these little i's are in a big set I, I'll talk about that in a second, is a cover of a set F in the reals if the following is true. If F is a subset of the union of the UIs, where all these i's come from the index set I. Okay? Another way of writing this, and I just thought about this now, is you could say this is the set of this is the union of the UIs, where the UIs are elements of the script U. So you just take all of the intervals in your collection, or all the sets in your collection, these UIs, and you take their union. Right? That's what we're talking about right here. Okay. So I just also want to draw your attention to I've got this index set here. Capital I is an index set. And so this is a way we say all the sets in our collection. Let me be more specific about this. In this definition, I is an index set. Okay? Its elements index or name the sets in the cover U. Okay? There is exactly one index for each set in the cover. Okay, that is to say there's a bijection between the sets in the collection, in the cover, and the elements in the index set. So we say a cover U is finite if its index set is finite. Okay, if its index set, and here the index set is I. So if that's a finite set, we say the cover is a finite cover. The cover U is infinite, and it could be uncountably infinite, it could be countably infinite, you can specify. But if it's infinite, if its index set I is infinite. So the cardinality of the index set gives us the cardinality of the cover. And remember, a cover is a collection of sets. So we're not looking at the number of real numbers that are in the cover. We're looking at the number of sets that are in the cover. Okay? So let me just go back. So I just explained to you what a cover is. Okay? Okay. And so I've just defined that term, what a cover is. Now I'm going to tell you what a subcover is. So let the collection U of sets of real numbers indexed by some index set I be a cover of a set F of real numbers. A subcover of the collection U is a subset of the collection U that also covers F. Okay? So if we say, or if we write our subcover to be U sub 0, which is a collection of the UI, UI in the collection U, where I is in some index set I sub naught, where I sub naught is a subset of I, it could be the whole thing, then U naught, it's a subset or a subcollection of U by the definition here that I've written down. But we say then U naught is a subcover if F is contained in the union of the UI, where I is in the index set for U naught. Okay. So if you have a cover of a set, a subcover of that cover is a subset of the original collection that also covers the original set. That's what we mean by a subcover. So I'll do some examples of some sets and covers and subcovers. But let's go back to here. Let's take this definition and we'll talk about it again. So a set F is compact if every open cover of F has a finite subcover. So to use this definition of compactness, you have to take an arbitrary subcover, right? Or an arbitrary cover, a cover that your worst enemy gives you, and demonstrate that you can find a subcover from it for your set. Okay? So let's do a couple important, simple examples of how this might work. So let's take the case where we have a real number x, okay, and let's consider our set f to be the singleton set. It just consists of that one number. Okay. So what would an open cover of this set look like? Okay. Well, let's just consider the interval AB with A being less than X and X is less than B. Okay. Under that condition, then we know X is in that interval. So notice if I make a collection that consists only of that interval I, then that collection is a cover of our set F. Okay. And I could say U naught, which is the whole thing, could be a trivial subcover. It's really our only choice. Okay. The subcover is the whole collection. So this is just an example of using the language of cover and using the language of subcover. It's really not telling us anything about the compactness of the singleton set. So to do that, let's ask our worst enemy for a cover. Oh, hey, one of the things I haven't talked about, I just realized, looking back at the definition, is the word open here. So let's just make sure we specify that definition. Let F be an R, and let U, consisting of a set of collection of UI, or let U be a collection of intervals or sets. Of real numbers. We say script U is an open cover of F if U is a cover of F and if all of the UI in U are open. So a cover is an open cover if it consists entirely of open sets. So that should be pretty straightforward. So let's go back to the example of a singleton set. Okay, so we'll just write this for clarity. Let F be our singleton set where X is a real number. Okay, and let's let UI be a collection of open subsets of the real numbers. Okay, and we'll let I be the index set for it. So, we don't want that I there. We want just script U. Let script U be this collection of open subsets of the real numbers, indexed by I. Okay, so it's going to be an arbitrary open cover of F. So what can we say about this open cover? Well, you can't say too much exactly, but what we do know is that X is a number that's in F, right? F just consists of the number X, but F is a subset of the union of all these open sets in our collection. By the definition of union, this means this means that X is in one of these elements. I'm going to call it U sub I naught. So let's define script U naught to be equal to U sub I naught. Okay. Then script U sub naught is a finite subcover, or finite, let's do this right, open subcover of U, right? Because X is in U sub I naught. This shows, so what does this just show? This shows that given any open cover, we can find a finite subcover. So given any open cover of this singleton set, we can find a finite open subcover of that singleton set. So this proves any singleton set is compact. And that's pretty cool. That's a good thing to know. So let's do another example. Let's consider F to be not just a singleton set, but let's just say it's a finite set of real numbers. Okay. Now let's let U be a collection of open intervals where they range through an index set. And let's let this be an open cover of F. Okay. So this means F is a subset of the union of these open UI where I is in the index set. Okay, that's what it means to be an open cover. So let's see if we can build a finite subcover. And don't mean to give away the punchline, but yeah, we can. And we do it almost exactly the way we did it with the previous example. So let's take one of the numbers in my set F, call it X sub j. So since U is a cover of F, there's some index k in the index set where X sub j is in the kth set in my collection. Okay, so let's rename k to be I sub j. That j goes along with the xj. Okay, repeat this for all the xj in F. So we get a collection script U naught equal, we get one open set for the first element of F, one open set for the second element of F, an open set for the third element of F, and all the way down to the last element of F. So we get these open sets. And here, xj, by construction, is in the open set U sub I sub j. Okay. Then, if we say I naught is the set of these indices, that's clearly a subset of I by construction. Right? And our U naught is a subset of U, is a subcover of F. Because of this. Because each of the elements of F is in one of these open sets. So if you look at F together, F is going to be contained in the union of all these open sets by construction. So what does this show? This shows F is compact. Another example of a compact set. Let me swipe back here for a second. I just want to point out here, when we started this, we started with an open cover that was arbitrary. We specified nothing about it. And in the course of the example, we just used properties of sets, properties of openness, really just properties of containment and properties of union, to demonstrate that our set F and the cover that we were given, we could extract a finite subcover from that cover. All right, so a finite set of singletons is compact. So let's do one more example. And I'm going to do an example of a set that's not compact. Okay, so not all sets are compacted. So let's consider the open interval 0 to 1. Let's take that as our set. And let's take this as our open cover. So let U be the collection of open intervals of the form epsilon to 1, where 0 is less than epsilon is less than 1. Okay? So if I want to write this collection down in set notation, I'd say U is the set of intervals of the form epsilon to 1 in R, such that epsilon is in a real number between 0 and 1. So this is our collection. It's an uncountable collection. Doesn't matter what the cardinality is. It's a collection. And we can see pretty easily this is an open cover of our set F. Okay? So why is that true? So let's show why it's true. So why is F a subset of the union of the epsilon 1s, where epsilon goes from 0 to 1? Well, so this is going to be a simple containment proof. So let's let X be in our set F. Okay? So X is between 0 and 1. All right. So what's the property? Since X isn't equal to 0, there is an epsilon naught in the reals between 0 and X. Okay. The interval epsilon naught to 1 is in our collection of open intervals, and X is in the interval epsilon naught to 1. Okay? This shows our collection U is an open cover of F. Okay? So we're set up for the conditions under which we would verify that our set F is compact. So if I can demonstrate that, well, what I'm going to demonstrate is that this open cover does not have a finite subcover, right? And so that would then show that F is not compact. So let's do that. So if F were compact, so this is going to be a demonstration by contradiction. U would contain a finite subcover, U naught. Okay? And so U naught would look like this. It would be a collection of intervals of the form epsilon to 1, and since it's a finite subcover, there'd be a finite number of these intervals. Okay, so let's let epsilon naught be the minimum of these epsilon i's. So it's the smallest left endpoint. Okay. So since all these epsilon i's are greater than 0, we know epsilon naught is also greater than 0. So consider a real number x that's between 0 and epsilon naught. We know they exist. There's lots of them. This x is in our set F, okay? But x is not in the union of the ui, where the ui come out of our subcover. Okay? Right? So what I've just demonstrated is that given any subcover, or purported subcover of my interval F, I can always find an element in F that's not in that subcover. Okay? That purported subcover. So this shows U naught cannot be a subcover of F. So no finite subcover of F exists. Therefore, F is not compact. Okay, so the interval from 0 to 1, the open interval from 0 to 1, is not a compact set because we showed there is an open cover of the set that doesn't have a finite subcover. Let me close by addressing one common misunderstanding about compact sets when viewed from the perspective of this definition. Let me paste the definition here if I can get it. Right, a set F is compact if every open cover of F has a finite subcover. What this means is that, and I'm repeating myself, but to show a set is compact, you need to take an arbitrary open cover and demonstrate that you have a way of finding a finite subcover from it. You can't choose any of the properties of the open cover. You have to take whatever is given to you and then extract a finite subcover from it. Sometimes people think, oh, I can just come up with an open cover and show that it has a finite subcover. But that's not the way it works. So to understand this a little bit better, let's take a look at the definition, write it out, and use propositional logic to see what its opposite is. So let's change this to blue. So a set is compact if for every open cover U, there exists a subcover that is finite. Okay, so this is the propositional statement that goes along with the definition. So let's negate this. So when you negate, you change the universal quantifier to an existential quantifier. So there exists an open cover such that the existential changes to a universal, such that for every subcover of the cover, and then any statement that follows, you negate that too. And so is finite is going to change to is not finite. All right? So this means there is an open cover for which every subcover must be infinite. Okay? Or you can say for which no finite collection is a subcover. Okay? So to show something's not compact, it's enough to find, just like we did in this last example, find an open cover that doesn't have a finite subcover, and that demonstrates the set is not compact. So to show something's compact, you need to be take an arbitrary open cover and demonstrate a way to find a finite subcover from it. All right, so I'll leave it there. I guess the parting shot will be that this is an important definition for compactness. It gives us some important tools when we're proving things. We might use that tool later in the semester, but if you go on and take a second semester of real analysis, or you take a course in measure theory or the theory of statistics, this is a technique that you will use. And it's a way to, compact sets in some ways mirror or have properties of finite sets, which is a cool concept. But because this isn't going to be central to what we're doing in the rest of the course, I decided to do a screencast on it, let you watch it on your own time. It's good if you watch this about the time we talk about the Heine-Borel theorem, but if you need to put it off a little bit, that's okay. But this is compactness defined in terms of open covers. See you next time.